Hi everyone, in this video I'm going to talk about the different in hybridizations. Okay, so let's start with the sp3 hybridization. The sp3 hybridization occurs when the central atom uses its atomic orbital from the valence electron to combine, okay, to undergo hybridization or to mix, right? When it's used, one of the s and three of the p is going to create sp3 hybrid orbitals. Okay, so there are going to be four new sp3 hybrid orbitals. So if you show them all together, this is what it's going to represent, right? So one of the sp3, two of the sp3, three of the sp3, and then four of the sp3. Okay, so we have like four of them. When shown together, it's going to represent as the tetrahedral geometry. Okay, so whenever that you see tetrahedral geometry, then you will need to know that that's going to refer as sp3 hybridization. Or you can use the number of electron domain as well. Whenever that you observe 4 electron domains, that is going to equal to sp3 hybridization. Okay, so now the central atom will use these hybrid orbitals, which is the sp3, right? They are going to overlap with another atom, such as hydrogen, for example. So that means in this case, if these contain, so these are the sp3 hybridization, right, on hybrid orbitals, and it's going to contain one electron, right, in order to be able to pretty much overlap with another atom. So if it's overlap with another atom, this is what it's going to form. Okay, so let's say it's going to overlap with this hydrogen atom with another hydrogen atom, right? So it's making the bond. So therefore, in this case, it's going to create a single bond, right? So that means in this case, the electron in the new hybrid orbitals sp3 is going to form sigma bond. The sigma bond represent a single bond. Okay, so whenever that you see single bond, it's going to be represented by the sigma bond. The sigma bond come from head-to-head overlap. Okay, so these two head-to-head overlap is going to creating that. Okay, so this is sp3 hybridization. Next, let's just take a look at the sp2 hybridization. When a central atom has the sp2 hybridization, it's going to use its atomic orbitals of the valence electron by using one of the s orbital and two of the p. Okay, so the geometry that is going to be represented would be similar to trigonal planar. Okay, so this is trigonal planar. Okay, so that clearly right there, that's trigonal planar. So pretty much each of these electron domain right here is going to represent the sp2 new hybrid orbitals, right? So this is going to be one of the sp2, another one of the sp2, and this is the third one of the sp2, right? Because you combine one of the s and two of the p. So total, the result of the new hybrid orbitals would be three of them. So 1, 2, and 3. Okay, so what happened is here that when you are combining one of the s and two of the p, you are going to have the p orbital left. Okay, so the p orbital that is left going to be on the on the y-axis. Okay, so it's gonna go up and down like this. Okay, so pretty much if you're looking at this, I'm going to actually put this into a whole molecule in just a few minutes here. So pretty much what you are going to have is that the bond that is going to overlap by using the sp2 hybrid orbitals is going to be sigma bond, right? Because these are going to be head-to-head overlap. Okay, so you're going to end up making 3 sigma bond, and the pi bond is left over. This is going to be side-to-side overlap of another molecule, okay, so of another atom. Okay, so I'm going to show you that later. But before we do that, let's take a look at this head-to-head overlap that forming the single bond first, or sigma bond, right? So in this case, this atom right here, for example, like carbon, this carbon right here that contains sp2 hybrid orbital is going to do head-to-head overlap with another atom, such as hydrogen atom, right? So if it's bond with the hydrogen atom, that is going to make a single bond, right? Or sigma bond in this case. Okay, so pretty much going to make sigma bond. Okay, so that means if you have another carbon atom, okay, that also contain sp2 hybridization, is also going to actually do head-to-head overlap with that as well. Okay, so that means in this case going to do that. Okay, so head-to-head overlap. And these carbon atom that contain sp2 hybridization also can bond to another hydrogen atom as well. Okay, so that means in this case you can just go right, put this on right here. Okay, so let me put that on. So again, so far what I'm looking at here is the overlapping by using the hybrid orbitals of sp2. Okay, so sp2 of the first carbon and sp2 of the second carbon that overlap with the hydrogen atom. Okay, so now let's take a look at the p orbital that empty. Okay, so the p orbital, the electron in the p orbital that we have not used yet, the p orbital that left over, if you look at this, is going to connect to each other by side-to-side overlap, right? So it's going to connect to each other by side-to-side overlap. So pretty much you are going to end up with connecting these two together because they are overlapping with each other. They're gonna forming the bond with each other. So this part right here, side-to-side overlap like this, that's what represent the pi bond. Okay, so that would represent the pi bond. Okay, so that means in this case, when you have sp2 hybridization, if you consider this carbon right here, you are going to end up with 3 sigma bond around it and then 1 pi bond. Okay, so same thing for this carbon too. You're gonna end up with 3 sigma bond, right? And 1 pi bond. Overall, this whole molecule would contain 1, 2, 3, 4, 5 sigma bond and 1 pi bond. Okay, so that's what this whole molecule would represent. Next, we are going to take a look at the sp hybridization. When a central atom use one of its s and one of its p orbitals to undergo hybridization, is going to create the sp hybrid orbitals that are going to result in 2 hybrid orbitals because you use one of the s and one of the p, right? So total would be 2 new hybrid orbitals. So this would represent sp hybrid orbital. This is also represent sp hybrid orbitals as well. So pretty much again, because the new hybrid orbital would form sigma bond, so therefore in this case, this hybrid orbital right here can form the sigma bond with hydrogen, which is the single bond, and also it can form another sigma bond with another atom that contains sp hybridization as well. Okay, so in this case, this atom also can connect or do the head-to-head overlap, right, to form the sigma bond as well. Okay, so because the sp hybridization, what we have is that you are going to have a linear geometry, right? So whenever that you see linear geometry, you are going to relate that to the sp hybridization. Because we are using only one s and one p, we are going to have 2 of the p orbital left, and those p orbital are going to be py and pz. Okay, so py would be on the y-axis like this. Okay, and because if you look at this, right, so this is represent the py. When py is left over with the 2 of them, right, because this also sp hybridization as well, they are going to do side-to-side overlap. Okay, so side-to-side overlap is going to create a pi bond. Okay, so this is what it's going to create. And you not only have py, you also have pz as well, right? Because you only use one of the p, right? You use one s and one p to create sp hybrid orbitals. You are going to have py left and also pz left. So that means the other orientation of the p orbital that left that did not undergo hybridization, or what we call unhybridized p orbitals, is going to also do the overlapping as well, right? So this would represent the the pz that we have left doesn't undergo hybridization, is also going to overlap by side to side, creating the pi bond as well. So that means in this case, what you are going to see as the result would be triple bond, the molecule that contains triple bond, right? So the triple bond molecule on the linear structure here, which is represented by the sp orbital, this atom would contain 2 sigma bond, right? Sorry, 2 sigma bond, because one from this sp hybrid orbital, the other one comes from this sp hybrid orbital, and also it can form 2 pi bond as well, right? So 1 and then 2 on this plane. Okay, so that means in this case, if you're looking at triple bond would contain 1 sigma and then 2 pi, right? 1 and then 2 pi. Okay, so overall, this molecule, if you count the overall number of bonds, this molecule right here would contain 1, 2, 3 sigma bond, and 1, 2 pi bond. Okay, so 1, 2, 3 sigma bond and 2 pi bond for this molecule because of that. Next, we are going to take a look at the rotation of the single bond and double bond and triple bond. Okay, so when you have single bond, okay, so this is single bond that represent the bond between carbon and another carbon. Okay, so these two carbon exhibit sp3 hybridization. Okay, because it's tetrahedral, right? So this is tetrahedral. If you consider this atom, this is also tetrahedral. If you consider this atom, right? So they both look tetrahedral. So the bond for the single bond can be rotated freely. Okay, so if you look at this, right, so you can pretty much like rotate these two freely. Okay. However, if you have double bond, okay, so let me find the geometry with the double bond, which is sp2, right? So this is the sp2 hybridization that this carbon has, right? Because it contains the sp2 hybridization that look like trigonal planar, right? So 1, 2, 3, okay. And then we have pi bond, right? So because if you think about sp2 again, it's use one of the S, two of the P, right? And then the fourth one would be the unhybridized, which is going to make the pi bond. Okay, so for this one, when you are having the pi bond, okay, the pi bond is going to restrict the rotation of the double bond. So that means in this case, I'm unable to like rotate it. I'm unable to rotate the bond between these two carbon, right? So that means the pi bond, the presence of the pi bond is restrict the rotation of the double bond. Okay, so that means double bond will not be able to freely rotate like what you see with the single bond that you see previously. Okay, same thing for the what do you call like the triple bond as well. Okay, so double bond cannot rotate. Triple bond also cannot rotate as well, so it's restrict that. But you can actually rotate like this, right? So that's not what we talk about. We talk about the rotation between these two. Okay, so we talk about these two rotation. We are not able to do that. Okay, because of the pi bond restrict the rotation of the double bond and also the triple bond as well.